This video is going to define and introduce logarithms. First, I'd like to think back to when we first talked about exponential functions. We graphed the function y equals 2 to the x by creating a table of values. If you'd like to see this done in more detail, you can reference an earlier video about exponential functions. But I've recreated the table of values that works for the function y equals 2 to the x. For example, if we take negative 2 and we plug that in for x, 2 to the negative 2 gives us 1/4. 2 to the negative 1 gives us 1/2, etc. And if I plot those points, I get the graph of my exponential function. This is exponential growth. Base is bigger than 1. It's increasing. We have a y-intercept of 1 and a horizontal asymptote at 0. Now, the question I want to focus on is this a one-to-one function, and does it have an inverse function? So is this a one-to-one function? The answer is yes. This function passes that horizontal line test, meaning if I draw a horizontal line through the graph, it will cross at most once. Another way of thinking about that is for this function, every single input, every x value, corresponds to a unique or a different output. Because this is a one-to-one function, that means it must have an inverse function. Our one-to-one functions all have inverse functions. And if I want to create the inverse of this exponential function, I would just switch the x's and y's. So on the left, here's my table of values for the function y equals 2 to the x. And if I go ahead and switch my x's and y's, so now my inputs are the 1/4, 1/2, 1, 2, 4, and the outputs of this inverse function are the things that were exponents, negative 2, negative 1, 0, 1, and 2. Switching the x's and y's is how I can define that inverse function. And the inverse of exponential functions is going to be defined as a logarithm. Logarithms are inverses of exponential functions. So the thing to notice is the inverse or the logarithm has outputs that correspond to exponents. So let's actually define our logarithm. And here's our definition. If I have the exponential function b to the x equals y, I can rewrite this in logarithmic form as log base b of y equals x. These two statements that I have on the screen are equivalent or identical. They give me the same information. So one thing to notice is that the base of our exponential is also the base of our logarithm. That's a little subscript on that logarithm. And then the thing that the exponential equals, this y, is the argument of our log. It's what goes inside our log. And then finally, the exponent is what that logarithm equals. And that's going to be a theme as we work with logarithms. I think one of the important things to remember is logarithms always give you exponents. Logarithms equal exponents. So let's see how this works by doing some examples. Let's start by just practicing writing in logarithmic form. Every single exponential expression or equation can be translated into a logarithm. And so I just put my definition over to the right. Log base b of y equals x is equivalent to b to the x equals y. I always like starting with the base. So this expression, 2 to the p equals 7, has a base of 2. So I'm going to write log base 2. Then the thing that the exponential expression equals goes inside my log. So I've got log base 2 of 7 equals the exponent, p. So 2 to the p equals 7 is equivalent to log base 2 of 7 equals p. Second example, again, I like to start with the base. So log base x, and then jumping over of m, equals the exponent, equals 3. Let's do one more. Start with the base. So base is 4. Log base 4 of 6 equals the exponent, equals x plus 3. So log base 4 of 6 equals x plus 3 is equivalent to 4 to the x plus 3 equals 6. Now, we should be able to go in the other order as well. If I give you a logarithm, we should be able to translate that into exponential form. Again, using that same definition, log base b of y equals x is equivalent to b to the x equals y. Once again, I always like starting with the base. The base is 3, and then what the log equals is my exponent. So I start with the 3 to the 2 equals y. So log base 3 of y equals 2 is equivalent to 3 to the 2 equals y. Again, notice the thing that the logarithm equals is my exponent. All right, one more. Start with the base. The base is 8. So 8 to the z equals x plus 4. Again, what the logarithm equals is always the exponent. So that means if we want to evaluate logarithms, we're going to be trying to find the exponent. Logarithms are exponents. Now, there's a couple of common logarithms that come up frequently in math and science. And the two logarithms that are pretty common are log base 10. And in fact, if we're working with a log base 10, we frequently don't write down the little 10. It's one of our common logs. So if you ever see a logarithm and you don't see that little base number, you can assume that it's base 10. The second logarithm that's common is log base e, where e is that natural number. It's an irrational number, so it's a decimal that goes on forever, but it's approximately 2.7. And log base e is often abbreviated as ln, and that stands for natural log. I would call this the natural log. So if you see an ln, that just means your base is e. All right, so now let's see if we can evaluate some logarithms. So in each of these problems, the trick, the key to working with logarithms is you're trying to find the exponent. So log base 2 of 8 equals, well, we don't know what it equals yet. So I always like rewriting these in exponential form. It helps me visualize what I'm actually trying to solve. So starting with my base is 2. So 2 to some unknown power equals 8. That's what we're trying to solve. 2 to what power equals 8. And then really it just takes a little bit of trial and error or thinking about multiplication and the times table. And I know that 2 times 2 times 2 is 8, or 2 to the third is 8. So that means log base 2 of 8 is equal to 3. Again, notice that answer is the exponent. All right, what about log base 3 of 9? In exponential form, the base is 3, so it's 3 to what power equals 9? We're trying to find the exponent that makes 3 a 9. Well, 3 squared is 9, so log base 3 of 9 has to equal 2. My next example says log 100, and the first thing I have to notice is there's no little number, there's no base written down, and so that tells me that this is actually a base 10 logarithm. So in exponential form, I am trying to solve 10 to what power equals 100? 10 to what power equals 100? Well, the answer is 2. 10 squared is 100. And in fact, base 10 logarithm is a common base because it gives you a nice measure of the order of magnitude of your number. So notice that 100 has 2 zeros. So 10 to the 2 is 100. If it was 1,000, 1,000 has 3 zeros. So 10 to the 3 would be 1,000. That exponent, that answer of the logarithm, is giving you a sense of how big that number is. All right, natural log of e. So first, when we see that natural log, that tells me that the base is e. So the problem I'm trying to solve here is e to what power equals e? Well, that would have to be a 1. E to the 1 equals e. So natural log of e turns into a 1. All right, let's do a couple more. Log base 2 of 1. The base is 2, so 2 to what power equals 1? And this is where we just have to remember that that 0 exponent always gives us an answer of 1. 2 to the 0 equals 1, so log base 2 of 1 is 0. And in fact, it doesn't matter what base you have. Anytime you take the log of 1, you're always going to get 0. And that's because anytime you have an exponent of 0, you're always going to get an answer of 1. So log of 1 is always going to equal 0. All right, what about log base 3 of square root of 3? That means 3 to what power equals square root of 3? So to solve this problem, we have to think about how can we rewrite that square root of 3 using an exponent. And the square root is the exact same thing as the 1/2 power. Square root of 3 is equivalent to 3 to the 1/2. So that means log base 3 of square root of 3 is equal to 1/2. If it was a cube root, it would be a 1/3 power, etc. All right, what about log base 5 of a fifth? So 5 to what power equals a fifth? Well, if our answer is a fraction like 1 over 5, that means we must have a negative exponent, and 5 to the negative 1 would be 1 over 5. Recalling that those negative exponents give us fractions or reciprocals. So let's do one more that's similar. 2 to what power is equal to a fourth? So base was 2. 2 to what power equals a fourth? Once again, I see that 1 over. That tells me it must be a negative exponent. And I know that 2 squared is 4, so it has to be negative 2. 2 to the negative 2 is 1 over 2 squared, or a fourth. So log base 2 of 1/4 is equal to negative 2. All right, I want to do a couple more. Let's simplify log base 2 of 2 to the 10th, and then see if we recognize a pattern that might be useful here. So we can solve this the same way as the other problems. 2 to what power equals 2 to the 10th? And so the only way I can make these two things equal is if I use the same exponent. The exponent has to be 10. 2 to the 10 equals 2 to the 10. So notice log base 2 of 2 to the 10 is equal to 10. Another way of thinking about this is log base 2 and 2 to a power. Those are inverse functions. That's how we defined our logarithm. And so because log base 2 and 2 to the x, or 2 to a power, are inverse functions, in a sense, they undo each other. And in general, we can say that if we have log base b of b to the x, notice the bases are the same, the answer has to equal x. So you can think of this log base b and b to a power almost as canceling each other out. They're inverse functions, so they're undoing the operation, and you're just going to be left with that exponent, that x. So log base 2 of 2 to the 10th has to equal 10. And using the exact same reasoning, natural log means we have base e. So we've got log base e of e to the 5. Well, that's going to have to equal 5. Has to equal the exponent. If we do these operations in the opposite order, the same thing is true. Again, exponential functions and logarithms are inverse functions. They do the opposite thing. So if we take b to the log base b of x, we're just going to be left with x. For example, 4 to the log base 4 of 3 should just equal 3. 10 to the, and this is actually a log base 10. Log 5 means log base 10. So 10 to the log base 10 of 5 would just equal 5. And again, that comes from the fact that logarithms and exponential functions are inverses. All right, that was my last example in this section. Let me know if you have any questions on this video.